Welcome to the DX Today podcast, your weekly deep dive into the AI ecosystem. I'm Rick Spair, and joining me as always is Laura.
Rick, I am so glad you brought me into this one because the story we are unpacking today might genuinely be the most underrated architectural news of the entire first quarter and a half of this year.
That is a strong claim, Laura, and I love that you are already pushing the stakes right out of the gate. Tell our listeners what we are talking about and why it matters this Sunday morning.
We are talking about Apple's ParaRNN, a paper that just landed as an oral presentation at ICLR 2026 in Rio, and it may quietly upend the dominant architecture story of the entire last decade of AI.
Okay, ICLR 2026 is one of the most prestigious machine learning conferences in the world, and an oral acceptance there is no small thing. Walk us through what Apple actually unveiled in Rio this week.
They unveiled a technique that finally lets you train classical recurrent neural networks in parallel, achieving up to a 665 times speedup over the old sequential approach to training them. That number is not a typo.
That speedup is enormous, but let me slow you down for the audience. Why does the word parallel matter so much here, and why has this been the fundamental bottleneck for recurrent networks since the very beginning?
Recurrent networks process sequences token by token, where each step depends on the previous step's hidden state. And that strict ordering meant you simply could not throw thousands of GPUs at training them in any efficient way.
So the irony here is that RNNs are wonderfully efficient at inference time, with a small constant memory footprint per token. But their training story has effectively been frozen out of the modern compute economy for years.
Exactly, Rick, and this is precisely why Transformers won the architecture war back in 2017, when the famous attention is all you need paper introduced an architecture that could actually be trained massively in parallel on GPUs.
Right, and once Transformers proved they could ride the GPU scaling wave to higher and higher capabilities, the whole industry pivoted. RNNs got shelved as legacy technology, and we have spent nearly a decade in a transformer monoculture.
That monoculture has real costs, though, and they have become very visible as context windows balloon. Transformer attention scales quadratically with sequence length, which is exactly why million-token contexts have gotten so expensive to actually serve.
That economic reality is showing up in everything from API pricing to data center energy bills. And it is exactly why state space models like Mamba started getting serious attention, because they scale linearly instead of quadratically.
Mamba and the state space model family were the first credible challenge, and they proved that a sub-quadratic architecture could really compete on benchmarks. ParaRNN essentially does the same thing, but for the original classical RNN family.
It's worth noting, too, that we have seen earlier hybrid attempts like RWKV that try to give you transformer-like training with RNN-like inference. But ParaRNN is the first time we have seen pure classical RNNs hit this scale.
That is a really important distinction, Rick. RWKV deserves credit for pushing the conversation forward, but ParaRNN works on standard GRU and LSTM cells without redesigning them, which makes it much easier for the field to adopt broadly.
Okay, walk me through how ParaRNN actually gets that 665 times speed up. What is the core technical insight that breaks the sequential barrier that everyone in the field thought was simply a fact of life?
They reframe the problem entirely from the ground up. Instead of viewing the sequence as a chain of recurrent computations, they cast all those nonlinear recurrence relationships as a single large system of equations to be solved together.
So they are essentially turning a step-by-step process into one giant simultaneous equation, and then they solve that system using a method that can actually exploit massive parallel hardware. That is a genuinely clever piece of framing.
It really is. They use Newton iterations, which is a classical numerical method that goes back centuries, combined with custom parallel reductions implemented in CUDA kernels that they wrote and optimized specifically for this workload on modern GPUs.
I love that Apple, of all companies, is doing fundamental open source GPU kernel work like this. That is not the stereotype most people have of their machine learning division. What did they actually train with this new framework?
They trained the first 7 billion parameter classical recurrent networks ever produced, specifically a parallelized GRU and a parallelized LSTM, and both reach language modeling scores that are competitive with transformers and the best state space models out there.
That headline result is the one that should be on every AI researcher's screen this morning, frankly. A 7 billion parameter classical RNN that holds its own against the transformer Pareto frontier feels almost dreamlike to those of us who lived through the 2017 transition.
It does feel that way, and the reason it matters is not just academic curiosity. RNNs at inference time use roughly constant memory per token, regardless of how long the context grows, which transforms the unit economics of long context inference completely.
Let me put a number on that for listeners. If a transformer has to hold a kilobyte of key value cache per token times 1 million tokens, you are talking about roughly a gigabyte of memory just for context bookkeeping per request.
That is right, and that gigabyte multiplies by every concurrent user you serve. With an RN, you are not maintaining a growing cache. You are updating a fixed size hidden state, which is fundamentally a different memory and energy profile altogether.
So in a world where everyone wants longer context windows, agentic workflows that hold lots of tool history and real-time multimodal streams, the inference economics of RNNs suddenly look very compelling for the next deployment phase of AI.
There is also an edge angle, Rick, that I think is essential to understanding the Apple story specifically. RNNs run beautifully on smaller hardware, which is precisely the regime Apple Silicon is optimized for in iPhones, iPads, and Macs.
That on-device alignment cannot be coincidence. Apple has been pushing private local intelligence as a clear differentiator from the cloud-heavy approach of OpenAI and Anthropic. And ParaRNN gives them an architecture that actually fits that strategy beautifully.
They even ship the framework with model checkpoints that run locally on Mac with Apple Silicon using their MLX framework, which is the clearest possible signal that this research is meant to feed real product roadmaps and not just papers.
Now, let me play devil's advocate for a minute, because every architecture story like this comes with but actually, that takes a year or two to surface. What are the legitimate skeptical reactions worth taking seriously here, Laura?
The biggest one is that being competitive on benchmarks at 7 billion parameters does not automatically extrapolate to 70 or 700 billion. Transformers have a famously smooth scaling curve, and we do not yet know if RNNs will too.
That is fair. Frontier models from OpenAI, Anthropic, and Google all live in that hundreds of billions of parameters territory now, and a 7 billion result, however clean, is still many doublings away from that frontier scale level of performance.
The second skepticism is around training stability at larger sizes. Newton iterations can be sensitive numerically, and the engineering effort to keep gradients well behaved at much larger scales is the kind of thing that breaks unexpectedly under stress.
So the proof point we should all be looking for over the next 12 months is whether anyone, Apple or someone else, can take ParaRNN to a 30 or 70 billion parameter model without things breaking down catastrophically.
Exactly that. And there is a third skepticism I take very seriously, which is that transformers benefit from a massive software and hardware ecosystem. Compilers, attention kernels, serving stacks, every layer is tuned for them, not for RNNs.
That ecosystem advantage is enormous and is the kind of thing that takes years and billions of dollars to replicate from scratch. Even a clearly better architecture does not always win when the existing one has that much momentum behind it.
Which is exactly why I think the open source release matters so much here. Apple is not trying to monopolize this technique. They are seeding it into the research community and inviting other labs to build on the framework freely.
That is a real shift for Apple, who historically has been famously closed about their machine learning research output. Putting CUDA kernels and 7 billion parameter checkpoints on a public GitHub repository is a meaningful cultural signal worth paying attention to.
It also tells you something about competitive pressure inside Cupertino. Apple is behind on frontier models compared to OpenAI, Anthropic, and Google, and one way to catch up is to change the architectural game rather than play their game.
Strategic judo, basically. If you cannot outspend the leaders on transformers, change the rules of the contest by introducing an architecture where your hardware advantage and your inference economics advantage actually matter more than raw parameter scale.
There is also a really fascinating implication for energy and sustainability that should not get lost. Inference is now estimated to consume more total compute than training across the entire industry. And RNN inference is dramatically cheaper per token at long contexts.
Which means if even a fraction of frontier workloads migrated from transformer-based serving stacks to RNN-based ones, we would be looking at a meaningful reduction in data center energy and a noticeably different carbon profile for the industry overall.
I want to be careful not to oversell that point too aggressively, though. Migrations like this take years, even when the math is favorable, and there is huge sunk cost in current serving infrastructure that nobody throws away on a whim.
Agreed completely. The realistic timeline is probably 18 to 36 months before we would see RNNs running production workloads at scale, and even then likely starting in narrow domains like edge devices and long context summarization rather than general chat.
That narrower entry point is actually how most architecture transitions happen historically. Convolutional networks did not replace fully connected networks overnight in the early days. They proved themselves on vision tasks first, and only then did the rest of the field follow.
The other historical parallel I keep thinking about is how Mamba quietly arrived in 2023, made some big benchmark claims, got a lot of skeptical reactions from the community, and yet continued accreting credibility through follow-up work and independent replication.
ParaRNN feels like it is at that exact same starting line right now this week. The benchmark numbers are real, the open source release is meaningful, and now the question is whether the broader research community can replicate and extend it.
For our listeners who do not write papers but who care about where AI is heading, what is the single most important takeaway from this story they should carry into their conversations this week with colleagues, customers, and friends?
I would say this very clearly to anyone listening. The transformer monoculture that has defined AI since 2017 is starting to fracture, and the next 5 years of deployment economics will likely look very different from the last 5.
And that fracturing matters because architecture choices ripple into hardware, energy, pricing, capability, and even what kinds of products are economically viable to build. We are watching a genuine fork in the road moment unfold in real time this spring.
One last thing I want to flag for listeners before we close out. The fact that this came out of Apple, not OpenAI or DeepMind or Anthropic, also says something interesting about where deep technical machine learning research is happening these days.
Apple, Meta, with their Llama work, and a growing constellation of academic groups are quietly producing some of the most consequential research, even though the headlines tend to focus on model releases and product launches from the usual frontier labs.
Which is a really good reminder that ICLR, NeurIPS, and the smaller workshops are still where the most important architectural work gets surfaced, even in an era where the loudest news is about product launches and giant funding rounds.
That is just a perfect place to land this conversation, Laura, and I'm grateful for your usual sharp analysis. The ParaRNN paper is open access. The code lives on GitHub at apple/ml-ParaRNN. And we will link the ARXIV paper in our show notes for anyone curious to dig in further.
I would strongly encourage anyone, even mildly curious, to at least skim the abstract and watch for follow-up papers in the coming months from other major labs. If classical RNNs really are back at frontier scale, the next 12 months are going to be one of the more wildly interesting stretches of architecture research we have seen.
That's all for today's episode of the DX Today podcast. Thanks for listening, and we'll see you next time.